Have you ever wondered if time travel is possible? Welcome to our deep dive into the mysteries of space-time. Today, we're unveiling 20 astonishing facts that will leave you questioning everything you thought you knew about the universe. From the mind-bending concept of every moment being predetermined to the eerie possibility of parallel universes, this video will stretch your imagination to its limits. So stay with us until the end. You will be absolutely amazed by the last fact. Let's journey through space and time together and uncover the secrets that lie beyond our everyday understanding. The second practice involves understanding what space-time is. Space-time, at its core, is the fusion of the three dimensions of space and the one dimension of time into a single four-dimensional continuum. This concept is fundamental to how we perceive and interact with the universe. Albert Einstein's theory of relativity revolutionized our understanding of space-time. According to Einstein, space and time are not separate entities but are interwoven into a single fabric. His famous equation, E equals mc squared, shows that energy and mass are interchangeable, fundamentally linking the physics of space-time. The theory also introduced the idea that massive objects like planets and stars cause a curvature in this space-time fabric, which we perceive as gravity. Imagine placing a heavy ball on a trampoline. The ball creates a dip and smaller objects placed near it will roll towards the ball. This is similar to how gravity works according to Einstein's theory. Essentially, space-time is a dynamic and flexible entity that shapes the motions of everything in the universe. The concept of the space-time continuum is crucial in modern physics because it provides a framework that unifies the dimensions of space and time, allowing us to better understand the universe's behavior. By treating time as a fourth dimension alongside our familiar three spatial dimensions, we can explain phenomena that classical physics could not account for. For instance, the space-time continuum explains how light travels at a constant speed regardless of the observer's motion, one of the key tenets of Einstein's special theory of relativity. It also helps elucidate why events that seem simultaneous from one viewpoint can appear sequential from another. This idea fundamentally challenges our everyday perceptions and helps scientists make precise predictions about cosmic events. The space-time continuum is also essential for understanding black holes. These mysterious entities warp space-time to such an extent that not even light can escape their gravitational pull. The continuum helps us visualize how space-time behaves near these incredibly dense objects, leading to insights into their formation and influence on the universe. Moreover, the space-time continuum is integral to cosmology, aiding in the study of the universe's origin, structure, and eventual fate. Without embracing this four-dimensional framework, modern physics would lack the tools necessary to explore these profound questions. The space-time continuum not only expands our comprehension, but also illustrates the elegance and interconnectedness of the universe. So, as we delve deeper into the mysteries of space-time, keep in mind how this concept underpins so much of what we know and don't yet know about the cosmos. The first fact involves the fascinating phenomenon of time dilation. Time dilation reveals that time itself doesn't flow at a constant rate. It can actually move slower or faster depending on various conditions like gravity and speed. According to Einstein's theory of relativity, time slows down in stronger gravitational fields and speeds up in weaker ones. This means that near massive objects like planets, stars, or black holes, time will pass more slowly compared to regions with less gravitational pull. An intriguing example of this is if you were to spend time near a black hole, you'd age more slowly than someone far away from it. Imagine an astronaut orbiting a black hole while their twin stays on Earth. If they reunite after the astronaut has completed their mission, they would find that the astronaut has aged less than their twin, a clear demonstration of time dilation. This effect is not just theoretical, it has been confirmed through experiments. For instance, precise clocks placed on airplanes and satellites show measurable differences in time compared to those on the ground. This phenomenon must be accounted for in the operation of GPS satellites, otherwise their positioning data would quickly become inaccurate. Time dilation also comes into play at high speeds. As an object approaches the speed of light, time for that object slows down relative to an observer at rest. If you could travel in a spaceship at near light speed, a short journey for you might equal years or even decades for those you left behind. This twin paradox, as it is often called, underscores how our intuitive understanding of time is challenged by the principles of relativity. In essence, time dilation shows us that time is not an absolute, unchanging entity, but a variable influenced by the fundamental forces of the universe. As we explore more about space-time, remember how such incredible phenomena reveal the underlying complexity and wonder of our cosmos. The second fact dives into the intriguing concept of how the fabric of space-time can be warped by massive objects. In essence, the presence of mass and energy distorts the fabric of space-time itself, much like a heavy ball placed on a stretched rubber sheet. This warping effect is what we perceive as gravity. Albert Einstein's general theory of relativity provides the framework for understanding this phenomenon. According to the theory, massive objects like planets, stars, and black holes cause a curvature in space-time. The more massive the object, the greater the distortion it creates. This curvature of space-time guides the paths of objects moving through it, essentially directing the course of planets, moons, and even light. Imagine holding a large sheet of fabric tightly at its edges and placing a heavy ball in the center. The ball creates a depression, and if you were to roll smaller balls around it, they would spiral towards the heavy ball, not because of any direct pull, but because the fabric itself is curved. This analogy helps us understand why planets orbit stars and why moons orbit planets. They follow the curved paths created by the warping of space-time around these massive bodies. Einstein's theory fundamentally changed our understanding of gravity. Before it, gravity was thought of as a force acting at a distance between two objects. However, the theory of relativity showed that gravity is a result of the warping of space-time. This means that rather than an invisible force acting across space, it's the very shape of space-time that dictates the movements of objects within it. One fascinating consequence of this warping is the gravitational lensing effect. When light from a distant star passes near a massive object like a galaxy or black hole, its path is bent due to the curved space-time. This bending can magnify and distort the image of the distant star, allowing astronomers to observe objects that would otherwise be too faint or obscured. Another profound implication is how black holes influence space-time. Black holes are regions of space where the warping of space-time becomes so extreme that not even light can escape. The boundary around a black hole, known as the event horizon, marks the point where space-time is so steeply curved that escape is impossible. Studying these regions provides important insights into the behavior of space-time under the most extreme conditions. Understanding the fabric of space-time and its warping by massive objects is crucial for modern astrophysics and cosmology. It helps us predict planetary orbits, understand cosmic events, and even navigate our spacecraft. This concept underscores the interconnectedness and elegance of the universe, showing us how deeply gravity is woven into the very fabric of reality. As we unravel more mysteries about space-time, we continue to marvel at its complex and beautiful nature. The third fact delves into the groundbreaking discovery of gravitational waves and their profound significance in the field of physics. Gravitational waves are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. Predicted by Albert Einstein in 1915 as part of his general theory of relativity, gravitational waves remained elusive for nearly a century. Einstein theorized that when massive objects like black holes or neutron stars accelerate, they disturb the space-time fabric, sending out ripples at the speed of light. Despite the theoretical foundation, detecting these waves proved extraordinarily challenging due to their incredibly faint nature. It wasn't until September 14, 2015, that the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct detection of gravitational waves. This monumental discovery confirmed Einstein's prediction and opened a new window into the cosmos. The detected waves originated from the merger of two black holes about 1.3 billion light-years away, an event so powerful it briefly emitted more energy than all the stars in the observable universe combined. The significance of discovering gravitational waves cannot be overstated. They provide a completely new way to observe and understand the universe, complementing traditional methods that rely on electromagnetic radiation such as light, radio waves, and X-rays. Gravitational waves carry information about their origins and the nature of gravity that cannot be obtained through other means. For instance, they allow scientists to study merging black holes, neutron star collisions, and even the formation of the universe itself in ways that were previously impossible. Furthermore, the detection of gravitational waves has led to the emerging field of gravitational wave astronomy. By using observatories like LIGO and its European counterpart, Virgo, scientists can now detect cosmic events with unprecedented precision. This ability to observe the universe through gravitational waves promises to answer fundamental questions about the nature of black holes, the behavior of matter under extreme conditions, and the dynamics of stellar collisions. In essence, the discovery of gravitational waves marks a revolution in our understanding of the universe. It validates key aspects of Einstein's theory of relativity and provides a powerful tool for exploring the most extreme environments in the cosmos. As we continue to develop more sensitive detectors and expand our knowledge, gravitational waves will undoubtedly play a crucial role in unraveling the mysteries of space-time. The fourth fact delves into the extraordinary influence of black holes on space-time. Black holes are regions where space-time is so intensely curved that nothing, not even light, can escape. This extreme warping is the result of a massive amount of matter being compressed into a very small area. Imagine a star that has exhausted its nuclear fuel and collapsed under its gravity, forming an incredibly dense point known as a singularity. Around this singularity is the event horizon, the boundary beyond which nothing can return. The gravitational forces near a black hole are immensely strong, causing significant distortions in space-time. One of the most intriguing effects of black holes on space-time is time dilation. Near the event horizon, time slows down dramatically relative to an observer far away. To an outside observer, it would appear as though anything approaching the black hole takes an infinite amount of time to reach the event horizon. However, for the object itself, time would seem to pass normally, highlighting the relative nature of time in extreme gravitational fields. Another fascinating phenomenon is spaghettification, also known as the tidal force effect. As an object gets closer to the black hole, the difference in gravitational pull between its near and far sides becomes so pronounced that it gets stretched into a long, thin shape, much like a piece of spaghetti. This effect beautifully illustrates how space-time behaves in the presence of such immense gravitational forces. Additionally, black holes produce gravitational waves when they interact with other massive objects. For instance, when two black holes merge, they send out ripples through the space-time fabric, which can be detected by instruments like LIGO. These waves carry information about the events that caused them, providing valuable insights into the behavior of black holes and the nature of gravity. Black holes also act as cosmic magnifying glasses through a process called gravitational lensing. Their intense gravitational field bends the light from objects behind them, magnifying and distorting our view of the universe. This enables astronomers to observe distant objects that would otherwise be invisible. Furthermore, some theories suggest that black holes might be gateways to other parts of the universe or even other universes entirely. While these ideas remain speculative, they highlight the profound impact black holes have on our understanding of space-time. In summary, black holes are more than just regions of intense gravity. They profoundly influence space-time, demonstrating the dynamic and flexible nature of the universe's fabric. As we continue to study these enigmatic objects, we gain deeper insights into the fundamental principles that govern our cosmos. The fifth fact explores the fascinating concept of wormholes, which are theoretical passages through space-time that could potentially allow for instant travel between distant points in the universe. Imagine folding a piece of paper so that two distant points touch, and then poking a hole through the overlapping points. This is a simple analogy for how a wormhole might connect two separate regions of space-time. Wormholes are solutions to the equations of general relativity, first proposed by Albert Einstein and Nathan Rosen, hence the name Einstein-Rosen bridges. Essentially, a wormhole is a tunnel-like structure with two ends, each located at different points in space-time. If these theoretical passages exist, they could enable shortcuts across vast cosmological distances. This idea is captivating because it suggests the possibility of faster-than-light travel, bypassing the conventional limitations imposed by the speed of light. However, wormholes come with significant theoretical challenges and uncertainties. One issue is their stability. According to general relativity, maintaining an open wormhole would require an exotic form of matter with negative energy density to counteract the immense gravitational forces that would otherwise cause it to collapse. This type of matter has not been observed and remains speculative. Moreover, even if stable wormholes could be created, their entrances might be surrounded by intense gravitational fields, making them hazardous to approach. Another fascinating aspect is the potential for time travel. If one end of a wormhole were accelerated to near light speeds and then brought back to its original position, time dilation could cause a different time to be experienced at each end of the wormhole. This could theoretically create a time machine, enabling travel to different points in the past or future. While the concept of wormholes is largely theoretical and remains unproven, it continues to capture the imagination of scientists and science fiction enthusiasts alike. The possibility of connecting distant parts of the universe or even different times reflects the profound and mysterious nature of space-time itself. As our understanding of fundamental physics deepens, we may one day uncover the secrets of these enigmatic structures and unlock new ways to explore the cosmos. The sixth fact delves into the intriguing thought experiment known as the twin paradox, which vividly illustrates the phenomenon of time dilation. The twin paradox involves a pair of twins, one of whom embarks on a high-speed journey into space while the other remains on Earth. According to Einstein's theory of relativity, as the traveling twin approaches the speed of light, they experience time much more slowly than their sibling on Earth. Imagine one twin embarking on a spaceship that travels at near light speed to a distant star, while the other twin stays behind. During this journey, the traveling twin's clock would tick more slowly compared to the clock of the twin on Earth. Upon the traveling twins' return, they would find that they have aged considerably less than their Earth-bound sibling. For example, if the spacefaring twins' journey lasted 5 years according to their own experience, they might find that decades have passed on Earth. This thought experiment starkly demonstrates how time is not a fixed and absolute entity, but a relative one that can vary depending on speed and gravity. The twin paradox is more than just a theoretical scenario. It has practical implications and has been confirmed through real-world experiments. Precise atomic clocks flown on airplanes and satellites have shown measurable differences in time compared to those left on the ground. This effect must also be considered in technologies like GPS, where satellites orbiting the Earth experience time differently due to both their speed and the weaker gravitational field compared to the Earth's surface. In essence, the twin paradox reveals the non-intuitive nature of time and challenges our everyday perceptions of its flow. By contemplating this paradox, we gain a deeper appreciation for the complexities of space-time and the profound impact of Einstein's theories on our understanding of the universe. This thought experiment not only underscores the fascinating effects of time dilation, but also invites us to rethink our notions of time, space, and reality itself. The seventh fact explores the intriguing cosmic censorship hypothesis, a concept that delves into one of the most mysterious questions in theoretical physics. Can naked singularities exist? Singularities are points in space where the gravitational field becomes infinitely strong, often found at the centers of black holes. According to general relativity, these points result from the complete collapse of a massive star's core. However, they are typically hidden behind an event horizon, making them inaccessible to outside observers. The cosmic censorship hypothesis, proposed by physicist Roger Penrose in 1969, suggests that nature censors these singularities, ensuring they are always cloaked by an event horizon. This means that the extreme conditions at the singularity's core never directly affect the rest of the universe. The idea posits that any singularity arising from realistic gravitational collapse cannot be naked or exposed. However, if a singularity could exist without an event horizon, it would challenge our understanding of the laws of physics and the structure of space-time. Naked singularities would expose the universe to infinite gravitational forces, potentially leading to unpredictable and chaotic outcomes. Investigating the cosmic censorship hypothesis has significant implications for our comprehension of the universe. If naked singularities can exist, they could provide insights into quantum gravity and the unification of general relativity with quantum mechanics. On the other hand, if the hypothesis holds true, it would reaffirm the stability and predictability of space-time as described by general relativity. Despite extensive research and numerous theoretical models, the existence of naked singularities remains an open question in modern physics. While some solutions to Einstein's equations suggest their potential reality, no conclusive observational evidence has been found. For now, the cosmic censorship hypothesis continues to be a captivating topic, inviting physicists to explore the boundaries of our knowledge and the fundamental nature of the universe. As we delve deeper into the enigmatic world of space-time, the question of whether naked singularities exist reminds us of the many unresolved mysteries waiting to be discovered. The eighth fact delves into the remarkable concept of the speed of light in space-time and why it is considered the ultimate speed limit in the universe. The speed of light in a vacuum, precisely 299,792 kilometers per second, is a fundamental constant of nature, often denoted by the letter c. This speed is not just an arbitrary number but a cornerstone in the framework of modern physics. Albert Einstein's theory of relativity posits that nothing can travel faster than the speed of light. This limitation arises because as an object approaches the speed of light, its mass effectively becomes infinite, and it would require an infinite amount of energy to accelerate it further. This principle sets a universal speed limit that governs the behavior of all matter and energy in the cosmos. The speed of light also plays a crucial role in defining the structure of space-time itself. It determines the maximum rate at which information and causal effects can propagate through the universe. This means that events occurring at one location can only influence other locations within a certain distance as time progresses, constrained by the speed of light. This limitation ensures that causality is preserved, preventing any paradoxes or violations of the natural order. Additionally, the speed of light influences the concept of simultaneity in relativity. Events that may appear simultaneous from one perspective can occur at different times from another, depending on the observer's relative motion. This relativity of simultaneity underscores how our intuitive notions of time and space are fundamentally altered at high velocities. The ultimate speed limit imposed by the speed of light also has profound implications for our understanding of the universe. It governs the expansion of space, the propagation of light from distant stars, and the communication between objects in space. For instance, the finite speed of light means that we see celestial objects not as they are now, but as they were when their light began its journey to us, sometimes millions or even billions of years ago. In essence, the speed of light is a fundamental aspect of the fabric of space-time, shaping our understanding of the universe and its limits. It highlights the interconnectedness of time, space, and the flow of information, providing a boundary that defines the behavior of everything in the cosmos. As we continue to explore the mysteries of space-time, the speed of light remains a key to unlocking the deeper secrets of the universe. The ninth fact delves into the fascinating relationship between space-time and GPS technology, highlighting how our everyday devices rely on the principles of relativity. GPS, or Global Positioning System, is an essential technology that allows us to pinpoint our location on Earth with incredible accuracy. However, what many people may not realize is that GPS technology wouldn't function correctly without accounting for the effects of relativity. GPS satellites orbit the Earth at an altitude of about 2,200 kilometers, moving at speeds of roughly 14,000 kilometers per hour. According to Einstein's theory of relativity, both the speed at which the satellites move and the weaker gravitational field at their altitude affect the passage of time. These effects lead to a phenomenon known as time dilation. In the satellite's frame of reference, time ticks slightly faster compared to the time experienced on the Earth's surface. If these relativistic effects were ignored, the time discrepancy would cause significant errors in the positioning data provided by the satellites. To be precise, the time dilation effect causes the satellite's clock to run faster by about 38 microseconds per day. While this might seem like an insignificant amount, it translates to positional errors of several kilometers over just one day. To ensure the accuracy of GPS, the system must account for both special relativity, which deals with the high speeds of the satellites, and general relativity, which considers the differences in gravitational potential between the Earth and the satellite's orbits. The onboard atomic clocks in the satellites are precisely adjusted to compensate for these relativistic effects. By doing so, GPS can provide location data with a precision of within a few meters. This intricate calibration underscores the practical implications of Einstein's theories in modern technology. Without the corrections provided by relativity, GPS would be rendered unreliable for navigation, mapping, and various other applications. The reliance on relativistic principles doesn't stop at just navigation. It extends to numerous fields, including telecommunications, scientific research, and even financial systems that depend on precise timing and synchronization. The implementation of relativity in GPS technology is a remarkable example of how advanced scientific theories translate into everyday conveniences, enhancing our ability to navigate and connect in the modern world. As we continue to explore and refine our understanding of space-time, these principles will undoubtedly facilitate further technological advancements, demonstrating the profound interconnectedness of fundamental physics and practical innovation. The 10th fact examines the tantalizing possibility of time travel, exploring various theories and their plausibility. Time travel, the idea of moving between different points in time much like we move through space, has fascinated humans for centuries. While many theories suggest intriguing possibilities, the practicality and feasibility of time travel remain subjects of intense debate among scientists. One of the most well-known theories comes from Albert Einstein's general theory of relativity, which suggests that time and space are interconnected, forming a four-dimensional fabric known as space-time. According to this theory, time travel could be possible through the warping of space-time. For example, traversable wormholes, theoretical passages through space-time, could potentially connect two distant points in both space and time. These Einstein-Rosen bridges might offer shortcuts across the universe and even allow travel to the past or future. However, maintaining a stable wormhole would require exotic matter with negative energy density, which has yet to be discovered or created in sufficient quantities. Another fascinating concept is the idea of cosmic strings, thin, high-density objects stretching across the universe. These strings, predicted by some models of the early universe, could warp space-time around them in such a way that traveling along specific paths near these strings might allow for time travel. However, the existence of cosmic strings remains hypothetical, and their stability is still under investigation. A more practical approach may involve the concept of time dilation, as illustrated by the twin paradox. Traveling at speeds close to the speed of light would cause time to slow down for the traveler relative to an observer at rest. This means that a journey that seems short for the spacefarer could result in significant passage of time on Earth. While this doesn't allow for backward time travel, it does offer a way to leap into the future. Quantum mechanics also presents intriguing possibilities for time travel. Some interpretations suggest that particles can influence each other across time, and phenomena like quantum entanglement hint at the potential for retrocausality, where effects can precede their causes. These ideas are still speculative and not yet supported by empirical evidence. Considerations of causality and paradoxes further complicate the concept of time travel. The classic grandfather paradox asks what would happen if a time traveler went back and prevented their own grandfather from meeting their grandmother, thus preventing the traveler's own existence. Solutions to such paradoxes include the possibility of parallel universes, where each action creates a new, divergent timeline, avoiding contradictions by ensuring that any changes made by a time traveler affect a different universe altogether. Despite the theoretical underpinnings, practical time travel remains elusive. The energies required, the need for exotic matter, and the unresolved paradoxes present significant hurdles. While time travel continues to be a captivating topic in science fiction and theoretical physics, the current scientific consensus is that it remains speculative and beyond our technological capabilities. In summary, while theories from relativity, quantum mechanics, and hypothetical constructs like wormholes and cosmic strings suggest that time travel might be possible in principle, the practical realization of these ideas faces substantial challenges. As our understanding of the universe deepens, we may uncover new insights that bring us closer to making time travel a reality. But for now, it remains an exciting frontier for exploration and imagination. The 11th fact delves into the mysterious nature of dark matter and its profound impact on space-time. Dark matter is an elusive substance that makes up about 27% of the universe's mass-energy content, yet it does not emit, absorb, or reflect light, making it invisible to current telescopic technologies. Despite being undetectable through electromagnetic radiation, its presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the most compelling pieces of evidence for dark matter comes from observing the rotational speeds of galaxies. According to Newtonian mechanics, the outer edges of a galaxy should rotate more slowly than the regions near the center, where most of the visible mass is concentrated. However, observations show that stars at the outer edges of galaxies are rotating at speeds nearly equal to those closer to the center. This discrepancy suggests that there is additional, unseen mass providing the necessary gravitational pull to maintain these high velocities. This unseen mass is attributed to dark matter. The influence of dark matter extends to the scale of galaxy clusters. These massive conglomerates of galaxies are held together by gravity. When we calculate the total mass of these clusters based on visible matter like stars and gas, we find that the gravitational binding is far stronger than what the visible mass alone can account for. This implies the existence of a substantial amount of dark matter within these clusters, exerting its gravitational influence. Dark matter also plays a crucial role in the formation and evolution of cosmic structures. During the early stages of the universe, dark matter provided the gravitational scaffolding around which ordinary matter could gather, leading to the formation of galaxies and larger cosmic structures. Without dark matter, the universe as we know it would not exist in its current form. To visualize dark matter's effect on space-time, consider its role in gravitational lensing. This phenomenon occurs when light from a distant object, such as a galaxy, passes near a massive object like a galaxy cluster on its way to Earth. The gravity of the intervening mass bends the light, creating distorted or multiple images of the distant object. Observations of these gravitational lenses often reveal more bending than what can be accounted for by visible mass alone, further indicating the presence of dark matter. Despite its significant influence on the cosmos, dark matter's exact nature remains one of the greatest unsolved mysteries in physics. Various theories propose that dark matter could be made up of unknown particles, such as weakly interacting massive particles or actions, which interact with ordinary matter primarily through gravity. Researchers are using sophisticated detectors and experiments to search for these particles, but so far, direct detection has eluded scientists. Understanding dark matter is crucial for a comprehensive understanding of space-time and the universe. Its pervasive influence touches every aspect of cosmic evolution, from the smallest scales of galaxies to the vast expanses of cosmic structure. As we continue to investigate the true nature of dark matter, we are not only searching for a missing piece of the cosmic puzzle, but also striving to unlock deeper insights into the fundamental workings of the universe. The 12th fact delves into the fascinating concept of space-time ripples, also known as gravitational waves, and what they reveal about the cosmos. Gravitational waves are disturbances in the fabric of space-time caused by some of the most energetic processes in the universe, such as the merging of black holes or neutron stars. When these massive bodies accelerate, they create ripples that spread outwards at the speed of light, carrying information about their origins. Imagine a stone thrown into a pond. The ripples that form on the water's surface are analogous to gravitational waves propagating through space-time. The detection of these waves was a groundbreaking achievement that confirmed a major prediction of Einstein's general theory of relativity. The first direct observation of gravitational waves took place on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, or LIGO, from the merger of two black holes over 1 billion light-years away. This discovery opened up a new way of observing the universe, allowing scientists to study cosmic events that are otherwise invisible through traditional methods like light and electromagnetic radiation. Gravitational waves offer a unique window into the violent and energetic processes that shape the cosmos. For example, they provide insights into the dynamics of black hole mergers, neutron star collisions, and even supernova explosions. The data carried by these ripples helps astrophysicists to understand the behavior of matter under extreme conditions, the nature of gravity, and the fundamental properties of space-time itself. One of the most significant revelations from gravitational wave observations is the confirmation of the existence of black hole binary systems where two black holes orbit each other before eventually merging. These events produce powerful gravitational waves that can be detected across vast distances, allowing scientists to pinpoint their locations and study their characteristics. Gravitational waves also hold the potential to reveal more about the early universe. Since they can travel through space-time almost unimpeded, they carry information from epochs that are otherwise inaccessible. This includes the moments just after the Big Bang, providing clues about the conditions and processes that shaped the universe's initial development. Moreover, the study of gravitational waves has given rise to the field of multi-messenger astronomy. By combining gravitational wave data with observations of light, radio waves, and other forms of electromagnetic radiation, scientists can gain a more comprehensive understanding of cosmic events. This interdisciplinary approach enriches our knowledge and enables the discovery of phenomena that might be missed by observing only one type of signal. In summary, space-time ripples or gravitational waves are a profound testament to the interconnectedness of the universe and its dynamic nature. They reveal the hidden workings of the cosmos, offer insights into extreme astrophysical events, and enhance our understanding of the universe's fundamental principles. As we continue to refine our detection methods and explore these ripples further, the secrets they unveil will undoubtedly deepen our knowledge of space-time and the cosmic tapestry. The 13th fact delves into the mind-blowing concept of the expanding universe, illustrating how space-time itself is stretching. It all began with the groundbreaking discovery by Edwin Hubble in 1929, which showed that galaxies are moving away from us and from each other. This observation led to the realization that the universe is not static but is expanding. Imagine dots on the surface of an inflating balloon. As the balloon expands, the dots move away from each other, not because they are traveling through space, but because space itself is expanding. Similarly, the galaxies are not merely moving apart through space, rather, the fabric of space-time between them is stretching. This expansion was further confirmed by the discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965. This faint glow of radiation which fills the universe is the afterglow of the Big Bang, providing a snapshot of the early universe. The observation of this cosmic microwave background radiation supports the idea that the universe has been expanding since its inception approximately 13.8 billion years ago. A fascinating aspect of this expanding universe is that it does not have a center. Every point in space is moving away from every other point, suggesting that the expansion is uniform throughout the cosmos. This challenges our everyday experiences and forces us to rethink our notions of space and distance. The rate of this expansion is described by the Hubble constant, a value that quantifies how fast the universe is expanding. However, recent observations have shown that the rate of expansion is not constant. In fact, it is accelerating, driven by a mysterious force known as dark energy. Dark energy is thought to make up about 68% of the universe's total energy, yet it remains one of the most enigmatic aspects of modern cosmology. The concept of an expanding universe also leads to profound questions about the ultimate fate of the cosmos. If the expansion continues to accelerate, it could lead to a scenario known as the Big Freeze, where galaxies move so far apart that stars burn out, leaving the universe cold and dark. Alternatively, if the expansion were to slow down and reverse, it could result in a big crunch, where the universe collapses back into a singularity. Understanding the expanding universe is crucial for our comprehension of space-time and the cosmos. It provides insights into the origins of the universe, the large-scale structure of the cosmos, and the forces that govern its evolution. As we continue to study the expansion of the universe, we not only delve deeper into the mysteries of space-time, but also advance our understanding of the fundamental nature of reality itself. The 14th fact delves into the mysterious phenomenon of quantum entanglement and its intriguing implications for space-time. Quantum entanglement, often described as spooky action at a distance, is a phenomenon where two or more particles become interconnected in such a way that the state of one particle instantly influences the state of the other, regardless of the distance between them. This concept challenges our classical understanding of space and time because it suggests a form of connection that transcends the limitations of space-time as we know it. To grasp this idea, imagine two entangled particles created in a lab. If one particle is sent to a distant location and the other remains nearby, any measurement made on one particle will instantly determine the measurement outcome of the other, even if they are light years apart. This instantaneous connection seems to violate the principle that information cannot travel faster than the speed of light, a cornerstone of relativity theory. However, quantum entanglement does not involve any transmission of information in the conventional sense, so it does not violate relativity. The phenomenon was first theoretically proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 and later experimentally confirmed. Despite Einstein's skepticism, famously referring to it as spooky action at a distance, entanglement has been demonstrated repeatedly in numerous experiments. One of the most profound implications of quantum entanglement is its potential connection to the fabric of space-time itself. Some physicists propose that entanglement could be the underlying mechanism that weaves space-time together at a fundamental level. This idea is part of an emerging field known as quantum gravity, which seeks to unify general relativity with quantum mechanics. For instance, the ER=EPR conjecture, named after the initials of Einstein-Rosen bridges and Einstein-Podolsky-Rosen paradox, suggests that entangled particles might be connected by tiny wormholes or Einstein-Rosen bridges in space-time. If true, this could offer a fascinating bridge between the quantum realm and the structure of space-time, providing new insights into the nature of reality. Quantum entanglement also has practical applications, particularly in the field of quantum computing and cryptography. Quantum computers leverage entanglement to perform complex calculations at unprecedented speeds, while quantum cryptography uses it to create virtually unbreakable encryption methods, ensuring secure communication. Additionally, researchers are exploring the possibility of using entanglement for long-distance quantum teleportation, where the state of a particle is transmitted from one location to another without physically traveling through the intervening space. Although current experiments are limited to relatively short distances, the principles underpinning quantum teleportation could revolutionize future communication technologies. In summary, quantum entanglement reveals a deeply interconnected aspect of the universe that challenges our traditional notions of space and time. It provides a tantalizing glimpse into the fundamental workings of the cosmos, offering potential pathways to unify the laws of quantum mechanics and general relativity. As we continue to explore the implications of entanglement, we may unlock new dimensions of understanding that reshape our comprehension of space-time and the very nature of reality. The 15th fact explores the monumental event known as the Big Bang, which marks the origin of space and time itself. The Big Bang theory suggests that approximately 13.8 billion years ago, the universe emerged from an extremely hot and dense state in an event that triggered the expansion of space-time. This primordial explosion didn't occur in space, rather, it created space and time as we understand them. Imagine the entire universe compressed into a single point, a singularity with infinite density and temperature. In an instant, this singularity began to expand, leading to the formation of all matter, energy, and the fabric of space-time. As the universe expanded, it cooled, allowing for the formation of fundamental particles and eventually atoms. Within the first few minutes, light elements like hydrogen and helium were formed through nuclear fusion in a process known as nucleosynthesis. This era laid the foundation for all the structures we observe today, from galaxies to stars to planets. The evidence supporting the Big Bang theory is compelling. One of the most significant pieces is the cosmic microwave background radiation, discovered by Arno Penzias and Robert Wilson in 1965. This faint glow, which permeates the universe, is the afterglow of the Big Bang, providing a snapshot of the early universe when it was just 380,000 years old. Another piece of evidence is the abundance of light elements, which matches theoretical predictions of nucleosynthesis from the Big Bang. Additionally, the redshift of distant galaxies observed by Edwin Hubble indicates that the universe is expanding, a crucial aspect of the Big Bang theory. As we continue to study the Big Bang, we delve into the fundamental questions about the nature of space-time. For instance, what caused the singularity to expand? Some theories suggest the influence of quantum fluctuations or the presence of an inflationary phase that exponentially expanded the universe in its earliest moments. The study of cosmic inflation proposed by physicist Alan Guth posits that a rapid expansion occurred fractions of a second after the Big Bang, smoothing out the universe and explaining its large-scale uniformity. This period of inflation stretched space-time itself, ironing out irregularities and setting the stage for the universe's subsequent evolution. The Big Bang also raises questions about what preceded it. Some theories suggest a cyclical universe that undergoes endless cycles of Big Bangs and Big Crunches. Others propose the existence of a multiverse, where our universe is just one of many born from a larger cosmic structure. These ideas highlight the profound mysteries that still surround the origin of space-time. Understanding the Big Bang is essential for comprehending the universe's evolution and the fundamental laws governing it. It provides a framework for explaining the distribution of galaxies, the formation of cosmic structures, and the behavior of space-time on the largest scales. As we continue to explore the origins of the universe, the Big Bang remains a cornerstone of cosmology, guiding our quest to unravel the ultimate mysteries of space and time. The 16th fact explores the cosmic microwave background, often referred to as the afterglow of the Big Bang. This faint glow of radiation fills the entire universe and provides a snapshot of the universe when it was just 380,000 years old. The cosmic microwave background, or CMB, is a crucial piece of evidence supporting the Big Bang theory and offers invaluable insights into the early universe's conditions. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, the CMB is the thermal radiation left over from the time when the universe transitioned from being opaque to transparent. During the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma where light couldn't travel freely. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, allowing light to travel unimpeded. This decoupling of matter and radiation resulted in the release of the CMB, which has been traveling through space ever since. The CMB is remarkably uniform, with tiny temperature fluctuations that are just 1 part in 100,000. These minute variations are incredibly significant as they represent the seeds of all current structure in the universe, from galaxies to clusters of galaxies. By studying these fluctuations, scientists can learn about the distribution of matter in the early universe, the rate of its expansion, and the fundamental parameters that govern its evolution. One of the most important missions to study the CMB was the Cosmic Background Explorer, or COBE, launched by NASA in 1989. COBE observations confirmed the CMB's blackbody spectrum, providing strong evidence for the Big Bang theory. Subsequent missions, such as the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck satellite, have mapped the CMB with increasing precision, offering detailed insights into the universe's early stages. These observations have refined our understanding of key cosmological parameters, such as the Hubble constant, the density of ordinary and dark matter, and the geometry of the universe. The CMB also provides clues about the mysterious phenomena of dark energy and the universe's accelerated expansion. By analyzing the data, cosmologists can test various models of inflation, a rapid expansion phase thought to have occurred fractions of a second after the Big Bang. Inflationary theories help explain the uniformity of the CMB and the large-scale structure of the cosmos. The study of the CMB continues to be a cornerstone in cosmology, revealing the intricate details of the universe's birth and its subsequent evolution. By decoding this ancient light, scientists gain a deeper understanding of the fundamental forces and events that have shaped the cosmos, offering a glimpse into the very origins of space and time. The 17th fact explores the mind-bending question of what existed before the Big Bang. The concept of time before the Big Bang is one of the most profound and perplexing mysteries in cosmology. According to the Big Bang theory, space and time as we know them began approximately 13.8 billion years ago with an immense explosion from an extremely hot and dense state. This event marked the creation of all matter, energy, and the fabric of space-time itself. However, the question of what, if anything, existed before this singularity is not only scientifically challenging but also philosophically intriguing. One popular theory is the idea of a cyclical universe, where the Big Bang was not the absolute beginning but part of an endless cycle of expansion and contraction. In such a model, each cycle ends with a big crunch, where the universe collapses back into a singularity, followed by a new Big Bang that initiates the next phase of expansion. This concept, often referred to as the oscillating universe theory, suggests that time extends infinitely into the past, with each cycle resetting the cosmic clock. Another theory posits the existence of a multiverse, where our universe is just one of many created from a larger, possibly infinite cosmic structure. In this scenario, the Big Bang was merely a local event within a vast multiverse, and other Big Bangs could have occurred in different regions, giving rise to other universes with their own distinct properties and laws of physics. This multiverse theory offers a tantalizing glimpse into the possibility that our universe is part of a much grander and more complex reality. Some physicists explore the notion of a pre-Big Bang state governed by quantum mechanics. According to this view, the universe could have originated from a quantum fluctuation in a pre-existing quantum vacuum. This quantum cosmology model suggests that the laws of quantum mechanics can describe the universe's earliest moments, where classical notions of space and time break down. In this framework, the Big Bang was a transition from a quantum state to the classical universe we observe today. Another intriguing idea involves the concept of cosmic inflation, an extremely rapid expansion phase thought to have occurred fractions of a second after the Big Bang. Some models of inflation propose that our universe emerged from a pre-existing inflating space, where quantum fluctuations caused regions to bubble off and create new universes, each with its own Big Bang. This eternal inflation model implies that inflation is an ongoing process, continuously generating new universes within a multiverse. Despite these theories, the question of what existed before the Big Bang remains largely speculative, with no definitive answers. The very notion of before may not even be applicable in the context of the Big Bang, as space and time themselves were created in that event. In this sense, asking what existed before the Big Bang might be akin to asking what lies north of the North Pole, a question that transcends the boundaries of our current understanding of space and time. In summary, exploring the concept of time before the Big Bang challenges our comprehension of the universe's origins and the nature of space and time itself. Whether through cyclical models, multiverse theories, quantum cosmology, or cosmic inflation, scientists continue to delve into these profound questions, pushing the limits of human knowledge and understanding. As we advance our theoretical and observational capabilities, we may one day uncover deeper insights into the true nature of the cosmos and its origins, shedding light on the ultimate mysteries of existence. The 18th fact delves into the captivating theories of the multiverse, proposing the existence of multiple dimensions and parallel universes. The idea of a multiverse suggests that our universe is not the only one but is part of a vast collection of universes, each with its own unique properties and laws of physics. These theories extend our understanding of space-time and open up new possibilities for the nature of reality itself. One of the most well-known multiverse theories comes from the realm of quantum mechanics. The many worlds interpretation posits that every quantum event spawns a new universe. In this framework, every possible outcome of a quantum decision actually occurs, but in separate, parallel universes. For example, if you were to flip a coin, the many worlds interpretation suggests that there is a universe where the coin lands heads and another where it lands tails. This theory implies an almost infinite number of universes, each branching off from every quantum event. Another compelling multiverse theory arises from the concept of cosmic inflation. Proposed by physicist Alan Guth, inflation describes a rapid expansion of space-time that occurred fractions of a second after the Big Bang. Some versions of this theory suggest that inflation didn't just happen once but is a continuous process, creating bubble universes in different regions of space. Each of these bubbles could represent a separate universe with its distinct physical laws and constants. This eternal inflation model implies that new universes are constantly being formed within a larger multiverse. String theory, a theoretical framework in which particles are described as one-dimensional strings, also predicts the existence of a multiverse. In string theory, there are additional dimensions beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions could be compactified or hidden in such a way that we don't perceive them, but they might allow for different types of universes. Some versions of string theory suggest the existence of a landscape of possible universes, each with its distinct set of physical parameters. The concept of parallel universes also appears in the study of black holes. Some theories propose that black holes could act as gateways to other universes. When matter falls into a black hole, it could potentially emerge in an entirely different universe, suggesting a profound interconnectedness between different regions of space-time. The idea of a multiverse challenges our traditional understanding of reality and raises intriguing philosophical questions. For instance, if parallel universes exist, what does that mean for free will and determinism? Are there versions of ourselves living out different lives in these other universes? These questions highlight the profound implications of multiverse theories for our understanding of existence and identity. While the idea of a multiverse remains speculative and largely theoretical, it is a tantalizing concept that pushes the boundaries of our knowledge. Advances in observational techniques and theoretical physics may one day provide evidence for or against the existence of parallel universes. As we continue to explore the nature of space-time and the fundamental principles that govern the cosmos, the possibility of a multiverse invites us to reconsider our place in the vast, complex tapestry of reality. The 19th fact delves into the profound concept of space-time symmetry and its pivotal role in physics. Space-time symmetry refers to the idea that the laws of physics remain invariant under certain transformations, such as shifts in position, rotation, and time reversal. This concept is foundational to our understanding of the universe and underpins many pivotal theories in physics. One of the most significant aspects of space-time symmetry is its connection to conservation laws. German mathematician Emmy Noether formulated Noether's theorem, which states that every continuous symmetry of the action of a physical system corresponds to a conservation law. For example, the symmetry of a system under time translation, meaning the laws of physics do not change over time, implies the conservation of energy. Similarly, spatial translation symmetry leads to the conservation of momentum, and rotational symmetry results in the conservation of angular momentum. These conservation laws are fundamental to our understanding of physical processes and the behavior of objects in the universe. Symmetries also play a crucial role in the development of quantum mechanics and quantum field theory. In these frameworks, particles and fields are described by wave functions or field equations that respect certain symmetries. These symmetries help predict the behavior of particles and the interactions between them. For instance, the concept of gauge symmetry underlies the standard model of particle physics, which describes the electromagnetic, weak and strong nuclear forces. Gauge symmetries explain why certain particles have the properties they do and predict the existence of other particles. The role of symmetry extends to the realm of general relativity, where the fabric of space-time itself is described by Einstein's equations. The symmetries of space-time, known as Lorentz invariants, ensure that the laws of physics are the same for all observers, regardless of their relative motion. This principle is critical for understanding the nature of gravity, black holes, and cosmology. One of the intriguing aspects of space-time symmetry is its potential connection to the unification of forces. Physicists seek a theory of everything that unifies all fundamental forces into a single framework. Symmetry principles are expected to play a key role in such a theory, revealing deeper insights into the nature of space-time, matter, and energy. Beyond its implications for physical laws, space-time symmetry also influences our understanding of the universe's structure and evolution. For example, cosmological models often rely on the assumption of homogeneity and isotropy, symmetries that suggest the universe is uniform and the same in all directions on large scales. These symmetries help explain the observed distribution of galaxies and the cosmic microwave background radiation. In summary, space-time symmetry is a cornerstone of modern physics, providing a unifying framework for understanding the fundamental forces, conservation laws, and the behavior of particles and fields. Its profound influence extends from the smallest scales of quantum mechanics to the vast expanse of the cosmos, highlighting the elegance and interconnectedness of the universe. As we continue to explore the mysteries of space-time, the role of symmetry will undoubtedly remain central to our quest for a deeper understanding of the fundamental principles that govern reality. The 20th fact delves into the future of space-time, exploring predictions and theories about what lies ahead for our universe. One of the most intriguing possibilities is the continued acceleration of the universe's expansion, driven by the mysterious force known as dark energy. If dark energy maintains its current influence, the universe could keep expanding at an ever-increasing rate, leading to a scenario known as the Big Freeze. In this distant future, galaxies will drift so far apart that interactions between them will become rare, stars will exhaust their nuclear fuel, and the universe will become a cold, dark place where only remnants of cosmic matter persist. Another possibility involves the concept of the Big Rip, a more extreme outcome of accelerated expansion. In this scenario, dark energy's repulsive force could grow so powerful that it eventually tears apart galaxies, stars, planets, and even atomic structures, leading to the ultimate disintegration of space-time itself. Alternatively, if dark energy were to decrease in strength, the universe might experience a big crunch, where gravitational forces overcome the expansion, causing the universe to collapse back into a singularity. This cyclical model suggests an endless series of expansions and contractions, potentially leading to new Big Bangs and new universes. Beyond these scenarios, the future of space-time might also be influenced by the discovery and understanding of new physical phenomena. Theories such as quantum gravity seek to unify general relativity with quantum mechanics, potentially unlocking new aspects of space-time that could revolutionize our comprehension of the cosmos. Advances in technology and observations may reveal hidden dimensions or exotic forms of matter and energy, providing deeper insights into the fabric of reality. Furthermore, the exploration of wormholes and other theoretical constructs could one day enable new methods of space-time manipulation, potentially allowing for faster-than-light travel or even time travel. While these ideas remain speculative, they highlight the boundless curiosity and imagination driving scientific inquiry. In summary, the future of space-time is a field rich with possibilities and challenges. As we continue to explore and understand the universe, our predictions and theories will evolve, shaping our vision of what lies ahead. Whether through the continued expansion, new discoveries, or revolutionary technologies, the journey to unravel the mysteries of space-time will undoubtedly lead us to profound and unexpected horizons. In summary, we have journeyed through some of the most astonishing aspects of space-time, from the mind-bending phenomenon of time dilation to the mysterious influence of dark matter. and from the reality-warping presence of black holes to the captivating possibility of parallel universes. These 20 facts not only stretch our understanding of the cosmos, but also challenge our fundamental perceptions of reality. The future of space-time holds even more mysteries waiting to be uncovered, and as we continue to explore, we are sure to encounter even more incredible discoveries. We hope you found these facts as fascinating as we did. We would love to hear your thoughts and which fact you found most mind-blowing in the comments below. Don't forget to like, share, and subscribe to our channel for more exciting content on space and mysteries. Thank you for joining us on this cosmic journey, and stay tuned for more explorations into the unknown.